Now for the course Introduction to Pure Mathematics, we look at the generation of new convergent series from old by alternating the signs of terms and introduce the idea of a power series.
The clarinet is playing the note C, and this is the same note on a tuning fork. Why should they sound so different? Well, let's look at the waveforms on an oscilloscope. The note from the tuning fork is a pure tone, and so we get an almost perfect sine wave, whereas the clarinet gives a much more complex waveform. The pure note is still there, but the clarinet sound includes other notes as well.
I'm going to try to simulate the sound of a clarinet using this synthesizer. Here's the pure note which we got with the tuning fork. On the oscilloscope it looks like this. Now we add in another note called an overtone. Here's the overtone. It's represented by a sine wave too, and we add it in. Now it still doesn't sound much like a clarinet, but we can continue to build up the note by adding in further overtones, albeit with smaller and smaller amplitudes. Here's the next one. Again, it's a sine wave. Adding in the sound, we get this. And so on. Here's the third, and the fourth. Each time, we are adding a higher yet softer note. Isn't that more like a clarinet? To get the sound, we had to add in more and more overtones. And in theory, we could have kept going forever, adding in more and more sine waves like this. But is it meaningful to add up an infinite number of functions?
Well, to add any number of functions, we should have to add their values at each point. So let's consider that problem first. Is it possible to add up infinitely many positive real numbers to produce a finite answer? We'll start with something you've met before, the series 1 plus a half plus a quarter and so on. We're going to represent the terms by areas. The first term is 1, and so the first partial sum is also 1. The second term is a half, so the second partial sum, S2, is 1 1/2. Then a quarter, so S3 is 1 3/4. Then an eighth, so S4 is 1 7/8, and so on. It looks as if the sequence of partial sums is converging to 2, but is it? Here's S1 again. That's 2 minus 1. S2 is 2 minus a half. S3 is 2 minus a quarter, and so on. For the nth partial sum, we have Sn equal to 2 minus 1 over 2 to the n. Does that help us to prove the series adds up to 2?
Yes, it does. We've just seen that Sn is 2 minus 1 over 2 to the n. Now, 1 over 2 to the n is a null sequence, so the limit as n tends to infinity of 1 over 2 to the n is just 0. And now I can get the limit of Sn from this line here. The limit as n tends to infinity of Sn is just 2 minus the limit as n tends to infinity of 1 over 2 to the n. So that's just 2 minus 0. So 2 is in fact the sum of this series. Let's look at another one, sigma 1 over n squared. Does this converge too? Again, we're going to represent the terms by areas. 1 over n squared is the area of a square with side of length 1 over n. So I can think of each term as a square. The first term is 1, and the second, the square of side a half. This is the third term, a square 1/3 by 1/3. So the third partial sum is certainly less than 1 plus a half. Now I can't put this next square here, so I'll start a new column. And the next 3 squares fit on top of that. And now I can see a strategy for dealing with this series. Here's the first term. So the first partial sum is 1. The next term is 1 over 2 squared. So S2 is 1.25. The third, 1 over 3 squared, can be piled on top of the second term, giving S3 as 1.3611. For the next term, a quarter squared, we begin a new column, and the fourth partial sum, S4, is 1.4236. And the next 3 terms can be piled on top. For the 8th term, we begin a new column of width 1/8. S8 is 1.5274, and we pile the next 7 terms on top of the 8th one, and then begin a new column with the 16th. Each new column is half the width of the preceding one, so we get columns of widths 1, a half, a quarter, an eighth, and so on. It looks as if sigma 1 over n squared is bounded by 2. Let's look at the sequence of partial sums again, but group the terms. S1 is just 1. S3 is 1.3611, and that's certainly less than 1.5. Similarly, S7 is less than 1 3/4. S15 is less than 1 7/8, and so on. So every partial sum is less than 2. Knowing that the partial sums are bounded, the monotone convergence theorem tells us that the sequence of partial sums is convergent. But this time, it's not at all clear what the sum is. All we do know is that it's less than 2. So what is it? Well, in the 18th century, Euler struggled with the problem for years, before finally he proved that the sum was pi squared over 6, and that's about 1.7. Well, if sigma 1 over n squared converges, what about sigma 1 over n? This is often called the harmonic series. Let's see what happens if we use a micro to find some terms. Here are the first 10. From them, it would appear that the series might converge, but appearances are deceptive here. And if we compare S10 and later partial sums, it looks as if it's divergent. So how can we prove that sigma 1 over n is divergent? Well, as before, we look at the sequence of partial sums. The first term is 1, so S1 is 1. Adding on a half, S2 is 1.5. Now the next 2 terms are a third and a quarter, and together they add up to more than a half. So S4 is greater than 1.5 plus a half. In other words, S4 is greater than 2. Now we take the next 4 terms. Together they contribute more than another half. So S8 is greater than 2 plus a half. That is greater than 2.5. And this process can be repeated as often as we like, provided we add in twice as many terms each time. So S16 is greater than 2.5 plus another half. And S32 is greater than 3.5, and so on. And in general, S2 to the power n is greater than 1 plus n over 2, and this tends to infinity. So the series sigma 1 over n is divergent.
Well, so far, we've met these 3 sequences. And from each of these sequences, we get a series. Here they are. Which of them converge? Well, this one, with typical term 1 over 2 to the nth, is convergent. we've seen that its sum is 2. This one is also convergent, although it's much harder to find its sum. We could get some idea of its sum with the help of a micro. But even a micro won't find the sum of this series because, of course, it's divergent. Now, these three are all null sequences. And it's certainly true that if a series is to converge, its terms must form a null sequence. But that isn't enough to guarantee that the corresponding series will converge. In mathematical language, we say that having a null sequence of terms is a necessary condition for the convergence of a series, but it's not a sufficient condition. However, there is one way in which you can use decreasing null sequences, and these are all decreasing, and guarantee we'll get a convergent series every time. Let's see how it works with this last series. What we do is to take the sequence of positive terms and then alternate the signs of the terms to form the series 1 minus a half plus a third minus a quarter, and so on. Here's the first term, and S1 is 1. The second term, a half, is subtracted, and so S2 is 0.5. To get the third partial sum, we add a third. So S3 is 0.8333 to 4 decimal places. Notice that S3 is less than S1. S4 is S3 minus a quarter, so it's this. Note that S4 is greater than S2, and so on. The even partial sums form an increasing sequence bounded above, the odd partial sums a decreasing sequence bounded below. Each sequence must converge by the monotone convergence theorem. But what about their limits? Well, the difference between consecutive sums is just 1 over n, and 1 over n tends to 0. The limit is therefore the same for both odd and even partial sums, and so the series does converge. In fact, its sum is log to the base e of 2. So by alternating the signs of this divergent series, we get a convergent one. And in general, if you start with any decreasing null sequence, it always turns out that the corresponding alternating series does converge. That's the basis of the alternating test. And for this reason, if we alternate the signs of the series sigma 1 over n squared, we get a convergent series. But we didn't really need the alternating test here, because, of course, sigma 1 over n squared is itself convergent. 1 minus a quarter plus a ninth and so on is absolutely convergence, and so it's certainly convergent. Now, sigma 1 over n squared was pi squared over 6. But what is the sum of the alternating series? As before, we'll record the odd and even partial sums separately. Here's the first term, and S1 is 1. Subtracting a quarter, S2 is 0.75. To get S3, we add a ninth to S2, and for S4, we subtract a 16th from S3, and so on. The even partial sums form an increasing sequence, the odd a decreasing one. Each sequence is bounded and so convergent. And because the difference between successive sums is the null sequence 1 over n squared, the limits must be the same. Therefore, the series converges. In fact, this time, the sum is pi squared over 12. Well, so far, we've looked at the series we get by alternating the signs of these two series. And we can do the same with this one, too. And, of course, we'll get another convergent series. But this time, we want to look at it in a different way. Ian?
Instead of thinking of this as 1 over 2 to the n with alternating signs, we could think of it like this. The series sigma minus 1 to the n over 2 to the n, and I've restored the powers of 2 in the denominators. This leads us to a different way of thinking about series. We could replace the minus 1 here by an x and get this. So the original series, sigma 1 over 2 to the n, is just this, but with x is equal to 1. And this series has x equal to minus 1. Series like this, with powers of x, are called power series. And like the series you've met so far, sometimes power series converge and sometimes they don't. So, can we put anything we like for x in here? Does this always converge? Or does it only converge for some values of x? Here's the series, sigma x to the n over 2 to the n, and I'll write it as sigma x over 2 to the power n. And when I do that, you can see that this is a geometric series, and the common ratio is x over 2. So this series will converge if the modulus of x over 2 is less than 1, which is the same as saying that the modulus of x should be less than 2. When the modulus of x is less than 2, this series converges, and its sum is 1 over 1 minus x over 2, which is equal to 2 over 2 minus x. And this is a function of x. So if a power series like this does converge, can we use it to define a function? In other words, could I have said that the function x maps to 2 over 2 minus x is the same as, or can be defined by, x maps to this power series? Well, provided that mod x is less than 2, it seems reasonable here. So let's have a look at another power series. What about this one? When does this converge? And if it does converge, can we use its sum to define a function of x? Well, let's tackle the convergence problem first. I'll use the ratio test. Remember that for the ratio test, I need to look at the limit as n tends to infinity of the modulus of an plus 1 divided by the modulus of an. And for this series, an is just x to the n over n factorial. So this ratio is the modulus of x to the n plus 1 divided by n plus 1 factorial, all divided by the modulus of x to the n divided by n factorial. Now we can do quite a lot of cancelling here, x to the n, and the n factorial takes out most of the n plus 1 factorial. And we're left with the modulus of x divided by n plus 1. And this tends to 0. So this series does converge for all values of x. In other words, this series does define some function of x. But what is this function? What does it look like? This time, all the partial sums are functions. The first one is x maps to 1. The next term is x maps to x. And adding the two together, we get the graph of x maps to 1 plus x. Next, we add in x squared over 2 factorial, and so on. Eventually, the extra terms will make very little difference, and the sum of the series of functions is this. What is this function? Well, you've seen graphs like this before. It looks like the graph of an exponential function, one of the form x maps to a to the x, and in fact it is. But what's the value of a here? To find the value of a, we'll put x is equal to 1, because a to the power 1 is just a. And the easiest way to sum this series is to use the micro again. And that gives us about 2.71828 for a. And that's a number we've met before. It's just e. So, when x is equal to 1, this series converges to e. And this function is just e to the x. This power series converges to e to the x for all values of x. And we could use this series as a way of defining e to the x instead of using the limit of 1 plus x over n to the power n that you met in the last unit.
Now that we've got this series for e to the x, what will we get if we alternate the signs of the terms? Well, 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial and so on is just what we'd get if we put minus x in here instead of plus x. In other words, alternating the signs here gives us just e to the minus x. And now, taking these two series, if we added them term by term, we'd get another power series. These x's would cancel, and so would the x cubed terms, x to the fifth, and so on, and we'd be left with just twice this constant term, twice the x squared term, and indeed twice all the even powers. If instead we now subtract the two series, then it's just these even powers which will cancel, and we're going to end up with twice the odd powers. In other words, a half of e to the x plus e to the minus x gives us the power series 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on. And a half of e to the x minus e to the minus x gives us this power series. And these two power series being convergent means that these two are also convergent for all values of x. And so they define two more functions. In fact, you've already met these two functions. They're just cosh and shine. These are the power series. Let's see what happens to the sequence of partial sum functions. Take cosh first. The first partial sum is 1. Then we get 1 plus x squared over 2 factorial, then 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on. Convergence to cosh x is very rapid. What about shine? The first partial sum is x, then we have x plus x cubed over 3 factorial, and so on. Again, there's rapid convergence, this time to shine x. So that's what the partial sums for these two power series look like. But previously, we looked at the series you get by alternating the signs of terms. What happens if we do that here? Well, here's the series for cosh x. And by alternating the signs, we get this series. Now, because cosh x converges for all values of x, this new series is absolutely convergent. But what function does it converge to? Let's start by looking at the partial sums. Here's 1. Subtracting x squared over 2 factorial, we get this. Adding x to the fourth over 4 factorial, we get this, and so on. We can see it converging to a very familiar graph. It's the function cos x. In fact, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on, is the power series for cos x. Now, we got this by alternating the signs of the terms of cosh x. What about shine? Well, here's the series we get. X minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on. This also converges for all x, but what's the function it represents? Here's the first partial sum, x maps to x. The second term is minus x cubed over 3 factorial, and so the second partial sum is this. And the third is this, and so on. If we continue this process, then once again we get a familiar graph. It's of the function sine x this time. And so you see, it does make sense to talk about the sum of an infinite number of functions. Sine x can be thought of as the sum of the functions x minus x cubed over 3 factorial, x to the fifth over 5 factorial, and so on. It's the limit of a sequence of polynomial functions corresponding to partial sums. You could even sum infinitely many sine functions. And of course, adding sine functions produces some much more interesting sounds.